So good evening everybody, and thank you for the invitation back to talk to High Legh Community Observatory. Two short talks this evening, the first of which is the ABC of stars and galaxies. How stars and galaxies are born, how they live, and how they die. So these two short talks were originally part of a series of 4 called The Universe Half an Hour at a Time. And this evening I'm talking about the ABC of stars, and then after a short break I'll talk about keeping an eye on the universe. So ABC, what do I mean by the ABC? Well, when we're thinking about galaxies, we want to ask ourselves, how do these structures come to be? We look out into the universe and we see these wonderful things. Some of them are spirals, some of them are less elegant than spirals, but the spirals themselves come in all shapes and sizes, different numbers of arms, different tightly winding spirals. In some cases, barred spirals. We can ask ourselves, how did all these galaxies end up looking the way they do? And of course, galaxies aren't just made of stars, they're made of other things as well, gas and dust, but for this talk we're just going to be thinking about the stars that make up galaxies and the galaxies themselves. So in terms of the ABC, I think for galaxies we can think of the ABC as being these 3. A stands for accretion.
Yeah, so it would be one of these things.
Would you mind just muting the microphone?
Oh, yeah.
Thank you. So A stands for accretion, because galaxies are formed by matter accreting or accumulating, if you prefer, under the influence of gravity. The B stands for black holes, because we believe that there are black holes, very massive, so-called supermassive black holes, existing at the centres of perhaps not all, but certainly a large number of galaxies that exist out there. Some of these black holes are feeding, matter is falling into them, producing a lot of energy. In other galaxies they are a little more quiet. And finally, the C of the ABC is for collisions, because galaxies evolve, they grow through collisions between galaxies and mergers between galaxies over many billions of years, and we'll see that happening a little later. In terms of the ABC of stars, I'm not going to couch it in quite the same terms, but let me just say one way that you can make a star. You can follow 3 simple steps to make a star if you want to do this yourself at home. You start with a very, very large cloud of hydrogen, preferably made in the Big Bang, but if you want to supply your own, that's okay. And if it's large enough, the 3 steps you need to follow are A, wait, B, wait some more, C, wait a little bit longer, and then you're done. Now you have a star. In other words, to make a star, all you really need is a large amount of hydrogen in the first place, and then you need to have the patience to let gravity do its stuff. So I'll say a slight take on the ABC a little later, but that's really all you need to know for the time being. How do we actually understand how stars and galaxies came to be? Well, some of it is through our basic understanding and trying to understand the laws of physics. But recently, a lot of our understanding of how the universe came to look the way it does is through simulations. In other words, starting with a computer model in which we try and say, well, if we start with this lump of mass and we let gravity do its stuff, can we explain the structures that then result from allowing gravity to take hold of matter and start to collapse matter into interesting looking structures? So on the largest scales, on the cosmic scale structure of the universe, we pretty much rely on simulations to tell us whether we think we've got the physics right or not. There are lots of simulations that have been running over the last 10 or 20 years. Here's just a little pastiche of a few selections that have been published in the last few years. In this particular talk, I'm going to borrow from a particular suite of simulations called the Illustris simulations, and I'm going to take some still images and some videos of that particular set of simulations to illustrate what I'm talking about. So we're going to start from the very early universe. If you go back far enough, everything that we currently see in the entire observable universe, all 100 billion light years of it, All of that used to be in a much smaller volume, a volume the size of a golf ball, just a few centimetres in size. It's rather mind-boggling to try and imagine all the stuff that is currently in the observable universe ever existing on such a small scale. But, as best we can tell, that's the way it was. And I like to think of this as a golf ball, not only because of that being roughly the right size, but because a golf ball has dimples in it. And these dimples represent small variations in the density of the early universe, and we can run our simulations with those small density variations present, and then we apply the laws of gravity, that the gravitational force between two objects depends on the mass and the distance between them. We simply run that simple idea and see how that chunk of mass behaves. In this case, we're taking a large cube of matter because that's the way the simulation prefers it, and we're just going to let gravity do its stuff over a few billion years and watch what happens. And because of these small variations in density, we find the structure collapses into a structure that looks like this, a web-like structure, with filaments and voids, and where these filaments seem to cross each other, we get little patches of high density matter, where the matter is collapsing into blobs. These blobs are ultimately going to be what we now call galaxies, and galaxy clusters and galaxy superclusters. It might take a few billion years to do that, but this is what the simulations tell us ought to happen if we have the right starting conditions. And when we look out into the universe, we do indeed see that galaxies seem to be spread throughout the universe, not uniformly, but in this sort of web-like structure. Now, these simulations aren't quite as simple as I would indicate. It's not just a question of take a lot of hydrogen, put in the rules of gravity, and then let it do its stuff. You have to take into account, if you want the details to be right, you have to take into account a lot of other factors. So we're talking about matter accretion, the right-hand panel, but when we're trying to calculate that, we have to take into account, for instance, the left-hand panel, the fact that the universe seems to be not only full of hydrogen, but seems to be full of a whole load of material that we're calling dark matter, even though we don't actually know what it is. Again, I told you about that back in 2019. In a sense, we haven't moved on much in the last 2 or 3 years because we still don't know what dark matter actually is. We know it's there, it has to be taken into account in these simulations, but we don't know what form it actually takes. And if we want the details of these simulations to be right, we also have to take into account the middle panel. As matter is contracting under the influence of gravity, once the densities become high enough, we can form stars, and stars are born and they live and they die, and at the end of a star's life it might go supernova and it might produce outgoing gas that will impede the infalling gas that we're trying to merge together to accrete to make the stars and make the galaxies. So it's not just gravity working unimpeded to make a galaxy. We have to take into account star-forming processes that can actually impede the infalling matter. So the actual calculation is quite complicated, which is why you need supercomputers capable of doing trillions of calculations a second, and then these programs might run for weeks or months in order to produce the sort of data I'm showing here. So if we take this cosmic web, and we're using the Illustris simulation here, you can perhaps see from the title this is called Illustris TNG. What does TNG mean? Well, Illustris had a successor, and instead of calling it version 2 of the simulation, in a little bit of irony, they decided to call it Illustris the next generation. So Illustris TNG is just shorthand for version 2 of this simulation suite. And if you want to see more images and more videos of how it all works, there's a little URL at the bottom of the screen there. I'll make handouts available later that you can follow up if you want to see more of these things. So we're going to look in detail at what happens where two of these filaments, or two or more of these filaments, meet, where you get a little high density region when gravity is doing its stuff, making the universe collapse. So what's going on in this white blob? Let's look in more detail at another of the Illustris simulations, this time on a scale of thousands of light years rather than millions of light years. So let's run the simulation a few billion years and see what's happening. Matter is falling through one of these filaments from the top, matter is falling from a filament to the left and from the right, and it's starting to collect into this sort of whirlpool structure that you can see in the centre here. Bright means more density, dark means lower density. And you can see various structures seem to be evolving. It's quite chaotic in the early stages. Sometimes you see a little what looks like a little satellite galaxy, and then it might get gobbled up by the main structure in the middle. We see other features coming in and sometimes disappearing again. But notice that the edges are now getting rather dark because most of the matter is being used up, and most of it is now concentrating in this central region, which I think you'll agree is starting to show the hint of a spiral galaxy. It's still got a little way to go, it's still a little bit ragged, it's still a little bit chaotic, but we can see how the infalling matter that comes from these filaments in the web can start to condense into these structures that we call galaxies. And of course, if we have a look out into the universe, some galaxies are very conveniently face on to our line of sight, and so we can see the spiral structure in all their majestic glory. In this particular case, not only do we see the spiral structure in enormous detail, but notice that we have these pink blobs pretty much everywhere around the galaxy. These pink regions are pink because hydrogen is glowing at this particular colour, and these are star-forming regions. These are hydrogen clouds which are producing a lot of new stars. This happens once the density of material gets high enough. Let's have a look at how that might happen. Some of these star clouds you're familiar with. For instance, here's a Hubble picture of the Great Nebula in Orion. That's what we're looking at when we see those little pink blobs in the galaxy. But again, to understand what's going on in the heart of a nebula like this, we have to run a simulation. This is a different simulation. This is one performed at the University of Exeter, where we're looking not at galactic scales, but we're looking on a scale of a few light years. We've taken a cloud of hydrogen. It happens to be spherical just because that's easier for the computer to work with. It doesn't really matter what shape it is. We've taken a cloud of hydrogen, and there again are small variations in the density, and also each little part of this cloud has been given a little nudge in a random direction to simulate the true random nature of hydrogen molecules roaming around the galaxy. So again, we're going to do the same thing. We start with a collection of matter, in this case a large cloud of hydrogen, and we're going to ask what happens if we let gravity do its stuff. So over a time period of perhaps a few million years, we can see that some of the cloud collapses, some of it might drift away. The brighter colours here indicate higher densities. And so you can see that gravity is starting to concentrate matter towards the middle, and when the matter is at a high enough density, it is possible for hydrogen nuclei to fuse and make helium. So nuclear fusion is the process by which lighter elements are fused into heavier elements, releasing energy in the process. And when these stars switch on, they are little white dots in this particular simulation. You can see that some of those stars simply remain close to where they're born. Other stars might get thrown out of this particular cluster. Notice that we started with enough hydrogen not to just make a few stars. We started with enough hydrogen, perhaps a few light years across, to make many thousands of stars. And that's how we think stars are often born, in clusters such as this. We're going to zoom out slightly just to give you a better idea of how this is arranged in three-dimensional space. Notice that the nice spherical hydrogen cloud is now looking a lot more ragged, but there's still quite a lot of hydrogen left. We haven't used up all of the hydrogen in order to make these thousands of stars. So this popcorn machine of stars being generated here, do we think that's a reasonable simulation of what reality looks like? In other words, if we take this particular result of a simulation, do we think that particular structure of having stars born in this way, do we think that's roughly what stars actually look like? Well, let's have a look at a star cluster. That's an actual star cluster imaged, and it does bear a striking resemblance to the sort of simulation that we were just looking at. So we're gaining some credence that maybe our understanding of how galaxies form and how stars form does seem that if we put the right physics into the simulation, it does seem to give us sensible sort of results. In terms of what's going on actually inside a star, I mentioned that when hydrogen has enough density, in other words, when gravity collapses hydrogen cloud and pushes all the hydrogens together, if it's hot enough and under high enough pressure, the hydrogen can fuse together to make heavier elements. But in terms of how a star lives, that's always a question of balance. So we could argue that in terms of the physics of what's going on, the ABC of stars, the B is the most important thing because it's a question of balance. Gravity is always trying to shrink this star. To start with, it's a large ball of gas. Eventually, it's a small ball of gas in which thermonuclear fusion is occurring at the centre. So gravity is always trying to contract the ball of gas, but once thermonuclear fusion occurs at the core and hydrogen fuses into helium, it releases energy and that radiation pours out from the core towards the surface, and in doing so it produces a pressure which opposes the force of gravity. In other words, all stars are a balance between gravity trying to crush the star and the radiation pressure from the nuclear reactor at the core trying to push outwards. When these two forces, radiation pressure pushing out and gravity pushing in, when those two forces are in balance, the star is stable, such as, for instance, our middle-aged sun. But if those two forces ever get out of balance, then the star must change, the star must evolve. And in fact, all of star birth, star life and star death can be explained in terms of this basic idea of, are the forces in balance or are things out of balance, in which case things have to change. It's useful to think of the way we classify stars. So here's, some of you may recognise this as a Hertzsprung-Russell diagram. It's a diagram in which we plotted stars on a vertical scale of their luminosity, and for convenience we choose the luminosity relative to the sun. This is the intrinsic brightness of the star, not how bright it looks in our night sky, but how bright it actually is. And on the horizontal scale we plot the sun's or the star's surface temperature. So there's our sun. The luminosity relative to our sun is of course by definition 1, and the sun's surface temperature is a little under 6,000 Kelvin or 6,000 Celsius or thereabouts. So that places our sun roughly in the middle of this Hertzsprung-Russell diagram, and that will be useful for what comes next when we look at how stars change during their life. So if we return to our cloud of hydrogen on the left-hand side, we've seen that when gravity does its stuff, it can produce stars because the compression of hydrogen ultimately can lead to nuclear fusion. If that produces a small star, and small in this context means something similar to our sun, then a star like that might live for many, many billions of years. Our sun is 5 billion years old, and it's probably got another 4 or 5 billion years ahead of it. In other words, the fusion of hydrogen to make helium is a process that releases enough energy to keep the Earth and other bodies in the solar system warm, but it still will last for many billions of years. When the fuel eventually does start to run out, remember the idea of balance. Gravity is balanced by radiation, but if the fuel starts to run out, gravity will win, in which case the star will start to compress. And when the star gets compressed, it heats up and will start to expand its outer atmosphere and become a so-called red giant. If the star doesn't have that much mass, it doesn't have enough gravity to hold on to that outer atmosphere, and the outer atmosphere can be lost into interstellar space. And we call that envelope that's been lost into space a planetary nebula. Not to be confused with planets in any way, that's just an anachronistic name based on when people first saw these objects, they were confused with planetary disks in the sky. So a planetary nebula is effectively a dead star in the sense that it's the star that's lost its outer atmosphere. And what's left at the very core is what used to be the core of the sun, the core of the star, which will then no longer be undergoing any nuclear fusion, but it will still be quite hot. So it's going to be small, perhaps only the size of the Earth or so, compared to the much larger size of the original star. And the white dwarf is hot, and therefore it's white, and it's a dwarf simply because it's small. If we look at where red giants and white dwarfs occur on our previous diagram, well, red giants are up here. They're much larger, they have a much larger surface area than our Sun, so they are more luminous, so they're further up the vertical axis. But they're quite cool, maybe half the temperature of our Sun, so they're further over to the right on the diagram. The hot core of the star that's exposed once the outer atmosphere has been blown away into a planetary nebula, the hot core is a white dwarf. It's relatively small, so it's not very luminous, so it's a little bit further down on the vertical axis, but it's quite hot, so it's further to the left than the Sun because it's hotter. Notice the scale runs from cold on the right to hot on the left of this horizontal scale. So if we return to this idea of stellar evolution, it is possible for the collapsing cloud to produce a small star which ends up as a white dwarf. But it might also produce a large star. In other words, it might be that more mass starts to collect together and then will start to undergo nuclear fusion. Remember the balance? Gravity has to be balanced by the nuclear reactions keeping gravity at bay. If we have a very massive star, there's a very strong gravitational force trying to crush the star, which means the star has to burn its fuel very rapidly in order to balance that gravitational force. So a very massive star doesn't last very long before it ends its life and starts to swell up into a red supergiant. What happens when the fuel eventually runs out? Well, it's possible that not only hydrogen can be fused into helium in large stars, helium can fuse into carbon or nitrogen or oxygen or silicon or heavier elements, but even so, eventually the fuel will run out. Once a star has fused elements into iron, it can no longer fuse iron into any heavier elements to release energy. Iron is the end of the road as far as a star is concerned. And when a star has run out of all of its fuel, if it's really massive, the core can collapse dramatically, catastrophically. The core of a massive star might collapse in a matter of seconds, and the resulting explosion can absolutely rip the star to pieces and produce a supernova, a remnant of which we can see here represented by the Crab Nebula. What happens to the very extreme core of this star after most of it has been blown away in a supernova remnant? Well, what's left is extremely compact, either a few kilometers in size. Remember, the white dwarf was about the size of the Earth. A neutron star would result if the compact object is only a few kilometers in size, perhaps the size of a city, something like that. And under extreme conditions, if the mass is compressed to a very small volume, it might produce a black hole, a region of space in which the matter is so heavily compressed, the escape velocity is so high that not even light can escape. So those are the ultimate fates of stars, white dwarfs or neutron stars or black holes, depending on the initial mass of the star that has been formed. One thing we have to remember is that although white dwarfs, neutron stars or black holes are what the star ends up as, along the way it's actually lost a lot of the material from the outer part of the star. The planetary nebula or the supernova remnant effectively are blown away from the original star and in a sense recycled back into the interstellar medium. So we might have started with a cloud of hydrogen and helium left over from the Big Bang. But once we've been through the process of making a star and then having the star come to the end of its life, that star will have produced some elements through nuclear fusion, and those elements will end up reseeding the interstellar medium, which gets enriched by these heavier elements. And then we end up with a cloud of hydrogen with a few heavy elements in it, and that will make new stars, which will go through this process again and make some more heavier elements, which again will be blown off into the interstellar medium, and this cycle will go round a few times. This must have already happened quite a few times, because when we look at the periodic table of the elements, when we look at all the elements that exist on Earth, we find lots of them, not just hydrogen and helium and lithium and beryllium. We find all sorts of things. So if we just dim that out, we started with hydrogen and helium from the Big Bang, but we know that there's lots of carbon and nitrogen and oxygen. Let's face it, we're made of those, so we know there's lots of those around, and we know there's lots of other elements in the crust of the Earth. And explaining where they all come from up to iron, that's part of the life cycle of stars. We would expect heavy stars to make a lot of the elements up to iron. But that doesn't explain where the heavier elements come from, like, for instance, silver and gold. They are heavier than iron, so they can't be made by stars during their lifetime. This is true, but when a star goes supernova, so much energy is released that it can make essentially all of the elements in the periodic table. And that explains where all the heavy elements come from that we see here on Earth. That's what happens to stars around us. When we look out into the night sky, the stars we see are relatively close, hundreds or perhaps thousands of light years away. But what's going on at the very centre of our galaxy? How do we know what's going on there? Well, recently it's been possible with modern telescopes to look at the heart of our galaxy, and it's been deduced that there are stars orbiting at the centre of our galaxy which appear to be orbiting around something that must be very massive, but which we can't see. Invisible but massive, that sounds like a black hole. So for some years, the stars at the centre of our galaxy have been monitored, and various stars have been tracked over a period of about a decade or so, and they've been observed to follow elliptical orbits, and by using essentially Newtonian mathematics, okay, with a little bit of Einstein thrown in, it's been possible to track all of these stars and deduce what must the object be at the centre of these orbits that's holding them into these orbits. By recording the positions and carefully measuring their positions, it's been determined that the object at the centre of our galaxy that's holding these stars in orbit must have a mass of not just a few times the mass of our Sun, but some 4 million times the mass of our Sun. The symbol there on the right, capital M, circle dot, is just a shorthand for the mass of our Sun. There's nothing special about the mass of our Sun, it's just a more convenient unit to use than to talk in kilograms or tons, for instance. So, it's a very massive object, but it's also a very small object. If it was any larger, these stars would be colliding with it. So it's a very massive object, 4 million times the mass of our Sun, but it must be smaller than our solar system. And it's been deduced that this must be a so-called supermassive black hole. Massive black holes are those with a mass of a few times our Sun, but if they are millions of times the mass of our Sun, then we refer to those as supermassive black holes. Now, we haven't directly seen the supermassive black hole at the centre of our Milky Way, but attempts have been made in 2019 to observe if we can see what's going on around a black hole in another galaxy, in this case the galaxy M87, Messier 87. Why not look in the Milky Way? Why look in another galaxy? Well, because it was deduced that the supermassive black hole in the middle of Messier 87 has a mass of not some millions of solar masses, but of 6.5 billion solar masses. So in other words, it is a huge supermassive black hole. Even on a scale of millions of solar masses, it's absolutely vast. So it was thought that it would be possible to image it using telescopes on Earth, using lots of radio telescopes as a large Earth-sized telescope. So what we're looking at here, this orange donut, is matter that's been heated as it's falling into the black hole. We can't actually see the black hole itself. The black hole is the sort of shadow, if you like, in the middle of this donut, but we're seeing light that's being generated because matter is falling into the supermassive black hole and is getting heated and is producing electromagnetic radiation, which we're now picking up. So we're not imaging it directly, but this is very convincing evidence that there must be a supermassive black hole in other galaxies, because that's about the only way we can explain why matter is behaving the way it is in this very hot donut of matter surrounding the black hole. When we look at a picture like this taken in visible light, we don't see any evidence of the black hole in the middle. That's because it's simply too small and it's lost in the glare of all the other stars in the neighbourhood of the centre of the galaxy. And when we look at lots of pictures like this, it's tempting to think that the galaxy is essentially a sort of a static structure. Yes, we know they're rotating like a Catherine wheel, and we can imagine that they turn once every few 100 million years. But we don't appreciate quite how dynamic a galaxy is and how it evolves over billions of years of its lifetime simply by looking at a lot of static images like this. When we look out into the universe, we find a lot of galaxies are interacting with each other. Here, the spiral arms of this galaxy are being perturbed by the fact that there's another galaxy in the bottom right there. But even with lots of snapshots like this, it's difficult to appreciate just what the role of galaxy interactions is in galaxy evolution. To understand that, again, we have to go back to our understanding of, let's look at a simulation of what we think galaxies will be doing and see if that gives us a prediction of what we would expect to see in the sky. When we do that, we realise that galaxies are very definitely not static objects. Here we see a few hundred or perhaps a few thousand galaxies, and we see them all interacting with each other over a spatial scale of millions of light years. There are two big galaxies right in the middle there. You can see them getting very close. They interact with each other, and then after a couple of passes, they actually merge together into one larger galaxy. And the more you look at these sorts of videos, every time I watch this video I see something different. Let's just run that again so we can get an idea of what's going on. Every time we look at this, we see that every galaxy is interacting with the other galaxies. Some of them are distorting each other, like the static picture I showed a moment ago. Some of them are eating each other. Some of these galaxies are cannibals, and large galaxies are absorbing smaller galaxies and growing as they do so. And we think this is an intrinsic part of galaxy evolution. That's how large galaxies come to be. And when we run a simulation like this, we can say, well, if that's the way it is, do we actually see this when we look out into our local neighbourhood of galaxies? Do we see a small number of large galaxies and a large number of small galaxies? We can run these simulations and we can test our ideas of the physics of how we think these things behave based on, do we end up with a universe that looks the way it does when we look out into the universe with whatever, the Hubble Space Telescope or any other ground-based telescope? Do we see the sorts of things that we get in these simulations? And that's how simulations help us understand the way the universe is put together. So just a reminder that when it comes to looking at stars, I haven't talked about the A and the C, but when we look at stars, the most important factor is the B of balance, that gravity is balanced by thermonuclear reactions in the core of stars producing radiation which balances the force of gravity trying to crush the star. If a star is in balance, it's happy. If a star gets out of balance, it evolves. With galaxies, I explicitly said that the ABC are A for accretion, because that's how galaxies form in the first place, by matter from the Big Bang accreting under the influence of gravity. Black holes are at the centre of most, if not all, galaxies. Some are very actively feeding on matter that's falling into them. Others are a little bit more quiescent. And finally, galaxies grow through collisions and mergers with other galaxies over periods of billions of years. We can't really tell that from just snapshots, but these simulations that I've been describing tell us how galaxies came to be and how they will continue evolving for billions of years to come. Thank you for listening.